The interactions and reactions of single atoms and molecules underlie the foundations of physical and chemical properties of materials. Surfaces provide a canvas to carefully design and tune chemistry or develop novel devices. And the ability to manipulate and understand matter at the most rudimentary level in order to realize atomically precise nanostructures is an extremely attractive prospect. Indeed, nanoscience and nanotechnology have generated a great deal of interest as the invention of new tools to probe and control matter at the spatial limit has driven new experimental investigations. A well-defined view of the complex interactions that occur within an atomic landscape is necessary to the realization of new, low-dimensional nanostructures that exhibit exciting new phenomena. In all respects, bottom-up fabrication methods that use self-assembly on a surface are governed by the interplay between intermolecular and molecule-substrate interactions. As shown here, with a bit of a caricature, a well-defined view of the intricate interactions between adsorbate molecules or materials and their chemical environments enables atoms, molecules, and even low-dimensional materials to be viewed as akin to Lego building blocks. I rely on two experimental techniques that are principally derivations of the scanning probe microscope, providing the ability to image individual molecules as well as capture their highly sensitive vibrational fingerprints in real space through a tandem approach. The scanning tunneling microscope, or STM, enables the real space imaging of surfaces at the atomic level. Although STM images appear topographic in nature, the apparent heights are a consequence of variations in the local density of states, which according to the Tursoff-Hammond approach are a convolution of the electronic structures of the tip, surface, and any adsorbed species. As a result, it can be difficult to define the binding orientation or conformation of non-planar flexible molecules with STM alone. Additionally, conventional STM lacks chemical sensitivity. In contrast, optical-based spectroscopies, such as Raman spectroscopy, can provide chemical information based on a vibrational fingerprint in nearly universal conditions. However, Raman scattering is a very weak process. Only about 1 in 10 million incident photons are scattered inelastically. Therefore, as an ensemble-based measurement, it does not readily lend itself to fundamental studies at the sub-nanoscale. And so I rely on a method that brings Raman spectroscopy into the near field. When an STM tip is made of a plasmonic metal, in my case silver, focused and coherent illumination results in a localized surface plasmon resonance at the apex of the tip. The highly enhanced and confined electromagnetic field enables tip-enhanced Raman spectroscopy, or TERS. By combining the spatial resolution of the SPM and vibrational fingerprints from Raman spectroscopy, TERS provides chemical information at the nanoscale with single molecule sensitivity. This has resulted in vibrant applications in studies of chemistry and structure in diverse conditions ranging from ultra-high vacuum to ambient, and even more recently to solution and electrochemical environments. In my research, I implement TERS in a cryogenic ultra-high vacuum STM system where the pristine and supremely stable conditions yield spectroscopic information with nearly atomic scale resolution. Light becomes confined to essentially a picocavity, leading to optical vibrational spectroscopy with about 1 angstrom resolution and tremendous enhanced Raman signal. This results in the ability to obtain full vibrational fingerprints of molecules and nanostructures with respect to highly localized effects. However, I need to mention that TERS spectra are determined by so-called selection rules. Due to the directionality of the enhanced electric field at the tip apex, it's oriented parallel to the tip and perpendicular to the surface. Vibrational modes with a substantial component perpendicular to the surface are most enhanced in a TERS spectrum. This facilitates the relatively easy identification of the binding orientations of non-planar molecules, but also implies that a planar molecule that lies flat on a surface typically yields minimal TERS signal. As a result, I rely on both STM and TERS to study surface-supported nanostructures composed of a range of building blocks. My PhD studies began when I joined the Jung Group in its second year, and as such, my first project was to develop optical coupling into the recently purchased UHV custom-built, variable temperature scanning probe microscope equipped with in-vacuo lenses. This schematic illustrates the home-built optical setup that allows the efficient coupling of lasers of multiple wavelengths to the tip sample junction via a combination of optical fibers and flipping mirrors. This maximizes the current and future flexibility of this system. The excitation and collection lenses are located inside the chamber on the STM stage, mounted on piezoelectric motors on opposite sides of the tip sample junction. By mounting the in-vacuo lenses on piezoelectric drivers, we are able to focus these lenses optimally and reliably for each sample and tip. Finally, the use of fiber optic coupling allows us to decouple the STM from the spectrograph and larger lasers that are housed on the optical table. Importantly, this minimizes vibrational noise that could interfere with STM and TERS imaging. Some TERS setups sacrifice the high-resolution imaging capabilities of STM in favor of optimizing optical coupling into the tip sample junction. However, the design shown here preserves the atomic scale imaging of the STM, resulting in a powerful tool to investigate surface-supported nanostructures. This first project shown here highlights the ability to use this instrument to combine both techniques. As shown in the top left, it was possible to obtain high-resolution STM images of self-assembled boron subthiocyane chloride molecules with atomic resolution of the adjacent silver 1O surface. The TERS spectrum, shown on the right, has an exceptional signal-to-noise ratio, permitting the clear identification of over 20 distinct vibrational modes. This strong vibrational fingerprint, shown in red, enables a direct comparison with a time-dependent density functional theory, or TDDFT, calculated Raman spectrum of a gas-phase sub-PC molecule, which is shown in blue. An overall spectral assessment reveals that the vibrational mode labeled here has a substantial blue shift in TERS spectra compared to the simulated spectrum. The calculated atomic displacement vectors reveal that this vibrational mode corresponds primarily to stretching of the axial boron-chloride bond, suggesting that a weak molecule-substrate interaction manifests primarily in this boron-chloride moiety. Although the structure of sub-PC is rigid and remains unchanged upon adsorption onto a surface, it is possible for the conformation of a molecule to change significantly when it interacts with a substrate. Polycyclic aromatic hydrocarbons can exhibit non-planar flexibility due to rotation about sigma bonds, or even flexibility within the carbon-carbon bonds that form their skeletal structure. This flexibility can result in unique binding conformations or orientations on surfaces. Here, I studied rubrene, an organic semiconductor with an exceptionally high karyomobility as a thin layer single crystal, on silver 100 with STM and TERS. Rubrene consists of a tetracene backbone with two phenyls on each side as shown here, where the tetracene backbone can twist and the phenyl moieties can rotate about their respective sigma bond to the tetracene backbone. STM imaging revealed the formation of three unique supramolecular assemblies, two types of molecular islands, as well as two molecule-wide molecular chains. By comparing TERS vibrational fingerprints with TDDFT simulations, with consideration for TERS selection rules, these three self-assemblies were found to be composed of two types of molecular binding conformations. Rubrene was found to adsorb either with the tetracene backbone perpendicular to the substrate, or with a flat orientation where the tetracene backbone lies parallel with the surface. TERS revealed unique vibrational fingerprints for each conformation. A rubrene molecule was found to adopt a flat orientation when surrounded within a molecular island, while a decrease in the density of intermolecular interactions results in a vertical orientation. The spatial resolution of TERS was tested by acquiring sequential spectra across the boundary of a molecular island and tracking the 1311 wave number vibrational mode that corresponds with a perpendicular orientation. As shown here, a TERS line profile results in angstrom scale resolution of the different binding orientations, matching the spatial resolution of STM in this case, and enabling the identification of the conformations of flexible molecules that lie adjacent to each other on a surface. When the interactions between molecules and a substrate are substantially strong, the surface can be used to catalyze chemical reactions. In the almond-like coupling reaction, aromatic precursor molecules containing aryl halides undergo dehalogenative coupling reactions via thermal activation on a metal substrate, yielding atomically precise nanocarbon structures. Although a leaving group, the halogen atoms can remain adsorbed on the surface and are typically considered to be an undesirable byproduct that can poison the growth process of nanostructures. Here, I instead found that halogen atoms can form highly localized chemical environments, modifying molecule-substrate interactions to steer stereoselective reactions. I studied the almond-like coupling reaction of 3,6-dibromophenanthroquinone, or DBPQ, on a Gull 100 surface. Following thermal annealing to 300 degrees Celsius, the leaving bromine atoms were found to form self-assembled islands and modify the surface reconstruction. Cis dimers formed on the bare gold surface, while trans dimers were observed within bromine networks, with near-total selectivity. With an increase in the annealing temperature to 375 degrees Celsius, polymeric chains were found to propagate from the bromine networks, while the cis dimers were found to terminate at S-shaped tetramers due to steric hindrance, suggesting the potential to purposefully use absorbed leaving groups as a tool to steer bottom-up fabrication methods. I would also like to briefly mention one last study, as an example of a future direction involving a heterostructure. Here, UHV-STM TERS was used to spectroscopically investigate a vertical organic borphine heterostructure. It was possible to identify the borphine phase beneath the adsorbates, as well as characterize interfacial strain in the borphine lattice that arises from molecular adsorption. This was confirmed by a combination of molecular manipulation with the STM tip and TERS vibrational fingerprints with angstrom scale spatial resolution. To conclude, the tandem technique of UHV-STM TERS enables unique investigations into the fundamental interactions that govern surface-supported nanostructures. Simultaneous atomic scale imaging and vibrational fingerprint information at the sub-nanoscale enable the study of the effects of highly localized environments on the molecules, materials, and chemistry that can be used to fabricate nanostructures. I would like to acknowledge my PhD advisor and mentor, Professor Nan Zheng, along with the other members of the Zheng Lab, who have contributed to many of the projects that are included in my PhD thesis work. And finally, I would like to acknowledge our funding sources and thank you for taking the time to watch my video.